It's my pleasure to welcome our second early career spotlight speaker. I've known Stefanie for a while, and I was thinking about the first time I met her. And I and my group, we were starting to dabble a little bit in sort of symbolic, more traditional AI things, and we realized that natural language would be a useful way to actually get at models that could help these robots do smarter things. And didn't really know much about natural language, and certainly in computational context. I had a grant that involved Deb Roy, and so we made an appointment to see Deb, and he couldn't make the meeting, but his grad student could. And we described what we were trying to do, and Stefanie said, I think I can help you. I didn't really realize what we were getting into, because Stefanie's motto is, you go hard or you go home. And so we got help, and we got a lot of help. Stefanie, over the course of the years that we worked together, figured out how to bring natural language into the planning systems that we were developing for our robots. She figured out how to formalize the problem, and she figured out how to make it work on real robots. She worked out that we were doing the math wrong, and after days at the whiteboard with Stefanie and my student Tom and myself, we worked out what then became the G-cube model, which I'm pleased to see is cited in several papers that have appeared here today, and that's a lot of, that is Stefanie's influence, changing how we think about this problem, and she moved the field. After that, Stefanie went from strength to strength, countless best paper awards. She became faculty at Brown in 2013. DARPA Young Investigator, or I guess it's the Young Faculty Award, NSF Career, Sloan Fellowship, et cetera. Won Best Paper at this conference in 2014 with Ross Nepper, which is a great accomplishment. And what I want to comment on is the thing that I really like about the work that Stefanie has done is that she's very technically rigorous. So in developing these algorithms, there's always a key component of like, what is the underlying insight, the technical insight that makes this work? And there's a deployment on the real system. So she has made her work in natural language understanding, work on a robotic forklift, on other ground vehicles, on aerial vehicles. She, working with the aerial vehicle group in my lab, made a quadrotor that you could talk to, which might be a stupid robot trick, but still it worked really, really well. It's my tremendous honor and privilege to welcome Stefanie to the stage and to thank her for many years of collaboration that we've had together. Stefanie.
All right, so I'm going to talk about learning models of language, action, and perception for human-robot collaboration. This is work that I've done with many wonderful collaborators in Nick's group. And in particular, I want to highlight Nakul Gopalan and Lawson Wong, who are around today if you want to learn more. So we are at a really exciting time in robotics. I was privileged to work on the forklift project when I was a postdoc at MIT in Nick's group. This was an autonomous robotic forklift that could drive around warehouses, pick things up, pick up pallets, and interact with people. And since that time, we've seen a tremendous amount of progress in self-driving cars operating on real roads. Waymo is doing unmanned testing in Arizona, and their big news is that they recently purchased 60,000 vehicles that they're going to turn into autonomous vehicles as this technology really has an impact in the real world. There's been a lot of progress for drones. This is the drone that I use in my course at Brown that we designed. It's the Pi drone. It's a Raspberry Pi Python autonomous drone. It costs $225 in parts, and all of it runs on board the Pi in Python. So your base station can be any old laptop, which is nice because you can let the person who you hand the drone to use an existing laptop. So this means you can have one robot per student. In a class, we're doing this with high school students and college students. This is the flight day from my class at Brown, where we tried to fly as many drones at once as we could. I should say this was funded by Amazon. Thanks, Ty. And in industry, this is happening through, the Skydio has done and made amazing product. You can buy it for a few $1,000s, a drone with 13 cameras, a stereo pair for each of the 6 sides of the cube, and it can fly autonomously. We bought one, and my son tried it out. He was running all around George's backyard, and it was autonomously following him, avoiding the tree, avoiding the deck, avoiding the other people. So autonomy is making very large, important, concrete advances in the real world. But there's a real question as we see these advances, how humans are going to interact with these platforms. How are they going to do what we want the robot to do and not what we don't want the robot to do? So we're going to start to see robots in our homes, in our hospitals, in our workplaces, interacting with us and interacting with our kids, interacting with our parents and with our grandparents. And so it's really important that we design interfaces that are easy for people to use. The sort of state of the art for all of the commercial robots I mentioned, including the forklift, which was a while ago, this is a picture from the forklift days, is something like a smartphone or a touchscreen interface. So when you use the Waymo, when you get in the Waymo cars, at least last time I did, there was a touchscreen that you put in where you wanted the car to go. And similarly for Skydio, there's a touchscreen that you say, I want it to follow this person. And then it goes on and operates autonomously. I'm envisioning a world where we have powerful, autonomous, collaborative robots, and we interact with them as if they were another person. So for example, if you were talking to the forklift, you might say in words, put the metal crate on the truck. And then the robot has to map between words in the human's language and stuff that's out there in the noisy, complicated, partially observed environment. This is a challenging problem because of the sort of impedance mismatch between this very compact and succinct language representation and the very high dimensional representation that the robot is trying getting from its sensors. And moreover, people don't like to restrict themselves to a fixed vocabulary and grammar. So even for this simple command, there's a tremendous diversity in the ways that people might give this sort of command to the robot. So for example, this is a video of the forklift putting a pallet on the truck. It's about 10 seconds long. It's really short. It's just going to go on loop. So it's going to start again now. And we asked people on the internet to give natural language instructions that they would give to a human operator to carry out the command that you see in this really, really short, dead simple video. And they said something like, put the tire pallet on the trailer, which is kind of what we expected. But they also said things like, place the pallet of tires on the left side of the trailer. So this person specified where they want the pallet of tires to go on the trailer. Not just any old place, but on the left side of the trailer. Another person said, lift tire pallet, move to an occupied location on truck, lower tire pallet, reverse to starting location, lower forks, end. So they kind of made up this programming language, and you know, a human could read that and you understand what they meant. They refer to stuff that's really there in the video. And in fact, when we look at the commands we got for this video, no two of them are identical. And all of them are kind of capturing different aspects of the robot's behavior. We don't see the same command twice. The challenge in natural language and robotics is to make a system that's robust to all of these natural language commands. So that was just one task, put the metal crate on the truck. But of course, people want a robot to do many more things besides just moving an object around. So you might tell the forklift something really low level, like move backwards 10 feet so I can get my pickup truck in the warehouse. Or you might tell your PR2 that's in a house, tilt the picture frame to the left a little bit. Okay, there, stop. You know, really fine-grained commands with a lot of interaction going back and forth. On the other hand, you might also want to say something very abstract. So for the forklift, you might say, move everything from receiving to storage. And then you go off and do something else, and the robot goes autonomously for an hour while it does that task. Or you might tell your home mobile manipulator robot, clean up, the house is a mess. And then you go to work, and you come home at 5 o'clock, and your house is clean. We want to be able to give these really high-level, abstract, autonomous commands. Finally, robots break a lot. They do not do what we want them to do a lot of the time. And for any powerful, autonomous, and collaborative robot, we need to be robust to these sorts of failures. We need to be able to take physical actions to recover from failures, but also social actions to recover from failures. So for example, if the person says, put the metal crate on the truck, and the robot can't understand, then the robot should figure out that there's actions it can take to recover from this failure. So it might do something like ask a question, which truck? And then the person points and says, that one over there. And then using that additional information, the robot can go off and continue to operate autonomously. So fundamentally, the problem that we want to solve is that people want to talk to robots about everything they can see and everything they can do, everything. And so if we want to have a successful natural language interface, then we need models of everything the robot can see and everything the robot can do. So the contributions of my research program is that I'm enabling human-robot collaboration by learning decision-theoretic models for communication, action, and perception. So the communication is about talking to the robot and the robot talking back using language and gesture. Because we know we want to talk to the robot about everything it can do, we need models of the robot's action that can connect to the models for language and gesture. And because we want to talk to the robot about everything it can see, we also need models for perception. So that's why we need to think about all three things: communication, action, and perception. By learning these models, we're going to be able to scale to really large problems by leveraging large data sets. And by using a decision-theoretic approach, we're going to be able to detect and then recover from failure, because the robot's going to reason about the uncertainty in its model of the world and what it thinks is going on out there. Together, we're going to be able to improve from experience. So in Maya's talk, I think she was hitting on a really important idea by pointing out that by adapting to a specific environment, you're trading off generality, but you're improving the accuracy. It's like a precision recall trade-off from the NLP world. You're trading off recall in exchange for more precision. And it's really important to ride that curve, because 90% accurate is terrible for a home robot that's putting away your dishes. That means every time it empties the dishwasher, it's always dropping 2 dishes. Go home. So we need to be able to be 99.999% accurate, and the only way we're going to get there is by riding that curve, improving from experience, whether that's by having humans program the robot or whether by having the robot learn from the data that's around. So the technical approach that I take is you sort of have a robot in the world with some objects. There's a control system. Perceptual data comes in and actions come out. This is straight out of probabilistic robotics. And we're going to augment the perceptual data with human input, like go to the truck, and communicative output, like asking questions. Which truck do I mean? And then inside the control system, the robot gets observations. It uses those observations to make some kind of model of the world. And then based on that world model, it takes actions. So I'm talking about a model-based approach here, because if we want language to connect to stuff in the robot's head, we need a model to connect to. So no policy. I'm happy to use policy-based methods where it makes sense, but we need models in the robot's head for the language to connect to. So then the question is, what kind of technical approach goes inside that control system? And the sort of answer that my group is using is partially observable Markov decision processes, POMDPs. So POMDPs are a graphical modeling framework for making decisions under uncertainty, where the robot makes the assumption, the Markov assumption, that the current state only depends on previous states. At each state, you get an observation of the environment, so you don't get to observe the state, you get to estimate the state. And then you get to pick an action. The action you pick at one time step affects the next time step. And then finally, we need a way to say what makes a good action. So you have a reward function that says, this is what's a good thing to do, and this is what's a bad thing to do. So POMDPs kind of have a bad reputation in robotics because they're really hard to solve. They're actually undecidable in the general case. But what I say is 2 things. One is something Leslie says, which is that the robot, it is a POMDP. And in the true case, it's a POMDP. So saying it's too hard is saying robotics is too hard, we should all go home. I don't think that's true. The other way that I think about it is to say POMDPs are like Python. Python, by the way, is also undecidable in the general case. So the question is, like, if I tell you I'm using POMDPs, it's something like telling you I'm using Python to program my robot. I've told you something, there's some good information there, but there's a lot more to the story besides just the fact that I'm using this programming language. You need to know the structure that's going to enable the problem to be solved in a tractable way. So in the case of POMDPs, the research question becomes, what are the assumptions, what is the representation for the random variables and conditional independence assumptions that are going to enable efficient learning and inference in this very general framework? So what I'm working towards in my research program is something I call the human-robot collaborative POMDP, the specific POMDP that's going to enable human-robot collaboration. So we're going to start with this general POMDP and then go towards a specific human-robot collaborative POMDP. So the first thing we're going to do is refactor the state to say that it's divided into the physical state of the world and the human's mental state. What does the person want? Then we're going to change the reward function to be, well, it's not just any old reward function. We want to do what the person wants, if only we knew what they wanted. So we're going to try to make, there's a lot of interesting things on deceptive robots, and it's very interesting, and it could go. But like, anyway, we're going to try to make happy robots that do what the person wants for this talk. And then we're going to refactor the observation model to say that there's physical sensors, cameras, and LiDARs, and microphones, and then there's social information, so language coming in from the speech recognition system, or gesture coming in from the person tracking system. So then we can look at this factor here, which is the observed language given the physical state of the world and the human's mental state. And this is talking about the problem of language understanding, which a lot of people in this community have worked on. We're trying to estimate what the person wants, given observations about the physical state of the world and what the person is saying. Then we can think about actions and reason about social actions, like asking a question, because it's going to change what the person's mental state is, and then that's going to cause them to give us more information, like the answer for the question later. So that's what I mean by communication for collaboration. So we can also think about the sort of physical action space. This is a very large combinatorial state action space, and we're going to need a lot of tricks in order to enable efficient inference in such a complicated action space, like hierarchical models. And that's what I mean by action for collaboration, the tricks that we're going to have to play in order to enable inference in such a large space. And then finally, we have to reason about the physical world given information from the robot sensors. And you might say this has nothing to do with collaboration. We'll just let the RSS people solve that for us and then plug it in. But actually, because of the need for robust perception and the need for perception that's tuned to the specific problem at hand, it's integrally tied with collaboration. So one of the examples I like to give is called the speck of dust problem. Robot, pick up that speck of dust on the floor over there. If I tell that to a person, they might not listen to me because they don't want me to do it, but they don't want to listen to me, but they would be able to understand that instruction. But if your robot was, in the beginning, always tracking all of the specks of dust everywhere it went, there is clearly not enough computational resources to do that. So we have to tune the perceptual system in order to enable effective collaboration. So that's perception for collaboration. So I could talk about any one of these for an hour, and I only have 25 minutes here. So what I'm going to do is use one example of communication for collaboration. It's sort of the simplest possible example, but it shows a fully realized language understanding robot in a POMDP setting, and then briefly give an overview of the work that we're doing in the other two areas. So this is a robot that's engaged in an object fetching task. So the idea is that the person wants the robot to deliver an object, and they're using language and gesture to say which object they want. So the person might say, can I have that bowl? And then you do a belief update, so you start out with a uniform distribution over the objects. And then based on the information from the language and the gesture, you figure out, oh, it's probably that bowl, and then the robot can hand it over. But if I move the person back, the same sort of instruction, can I have the marker, is much more challenging. The reason is that the gesture is hard to interpret when you're farther away. So now the robot isn't sure which of the two markers that it's supposed to hand over. So what we'd like for it to do in this case is to decide that it needs to gather more information and then based on its belief state, and then automatically decide what questions to ask in order to follow these instructions. So what we did is we created a model that we called the Fetch POMDP, Feedback for a Collaborative Handoff. This was at ICRA last year, that enables the robot to reason about its uncertainty over what object the person wants, and then intelligently decide to ask a question, this one. And then based on the information from the answer, the person says no, the other one, we do another belief update, and the robot is now sure, and it can hand off the correct object. So I'm going to show you a video of what this looks like on the real robot.
Can I have that bowl?
Final answer. You wanted object 4.
So this is the unambiguous case. So this is the model running when we're really close, and that gesture is just perfect. The robot very quickly and autonomously decides, I know what you want, and I'm going to hand it off to you. We're just pointing to make the resets faster. So now we're going to move the person back. It's going to be more ambiguous. The same code. There's no code changes in between these two videos.
Can I have the metal object over there?
This one?
No, the other spoon.
Final answer. You wanted object 6.
So this is the ambiguous situation. The robot automatically decides it needs to ask a question, and then based on the information from the answer, it automatically decides, I know what you want, and hands it off. We did a user study, which I don't have time to talk about in detail, but the sort of short story is that using this POMDP method is 25% faster. It's about 2 seconds faster, and 2% more accurate than an average of baseline methods that don't intelligently decide. And actually, this model is a keyword-based model. There's no spatial prepositions. There's no parsing, even though I believe in all that and I want to do all that. This model had none of that. And despite that, 38% of our users thought the system could understand prepositional phrases like to the left of and to the right of, even though it had no idea. It was ignoring those words. And the reason we think is that the interaction, the back and forth, was so natural that they kind of assumed the robot could do things that it actually couldn't do. So we can kind of look back at the human-robot collaborative POMDP and say, well, actually, what's going on inside this language is we're using not just one monolithic factor for language, but there's a keyword-based language model that's going on here. And actually, Nick was talking about our G-cubed work. I believe it's really a compositional language model. And I don't have time to talk about the other direction of asking questions or asking for help. But just, this was at RSS a couple years ago, where the robot it could say, help me when it gets stuck, but that's really hard for the person to know what to do to help this robot. These are IKEA robots assembling furniture, and this was joint work with Ross Knepper. And so instead, we could say, please hand me the white table leg. But there's 3 white table legs in this scene. It's not clear which one the robot should do. So by doing some more tricks with compositional semantics, we can automatically generate a context-specific request for help. Hand me the white leg that's on the table. And then we showed that this works better at enabling the robot to help the person. So this sort of shows that the action space also can factor compositionally. So now I'm going to talk briefly about our work on trying to understand natural language commands at different levels of abstraction. So sort of going back to the POMDP setting, what we want to be able to do is understand really fine-grained commands. This is an example from a grid world where the robot can move stuff around and push objects. And we'd like to be able to say, go down 5, right 5, really low-level commands, and also take the red chair to the blue room, really high-level commands. So low-level instructions, you sacrifice granularity. You can't say those fine-grained things. But high-level instructions, but high-level instructions sacrifice granularity, and low-level instructions don't work in really big, complicated environments like the International Space Station. So our approach was to basically make the robot map between language and reward functions at different levels of abstraction using this hierarchical model, abstract Markov decision processes. So going back to the POMDP, this action space is not just compositional, it's also organized in a hierarchical framework that enables efficient learning and inference. So when it looks like on the real robot,
go to the red room.
We can understand a command like go to the red room, so it's running its inference, inferring a goal. And then the same command
Go south, south, south.
in a lower level representation with no code changes. It can just automatically understand both sorts of commands. So I'm going to skip some slides because I think I'm running out of time. But so basically, so that's sort of action for collaboration, this hierarchical abstraction. And then the final thing I just want to shout out to is perception. So we have some work making robots do robust perception in complicated environments. So I got frustrated by fiducial systems, even though I used them a lot too, and how they couldn't generalize. When we really want robots to do precise manipulation in, so for example, we'd like Baxter to pick up this nut and screw it in the bolt, or handle highly non-Lambertian scenes. So for example, picking this fork out of a sink filled with running water. And we came up with a new approach based on light fields that turns a camera that moves, a monocular camera that moves, into a time-lapse light field camera. And that enables the robot to automatically pick a fork out of running water using the Baxter's monocular camera to localize the fork. This is showing this running 24 to 25 times, successfully picking the fork. So to finish up, so perception for collaboration. So to finish up, we started off with this sort of really spare POMDP model, and then piece by piece, we added more pieces in order to create this richer framework that enables more efficient learning and inference in these different pieces. And this is sort of an aspirational slide in some ways, because many of these papers are sort of doing one thing and not the other thing. So going forwards, what I want to do is make this all happen on one robot in one big POMDP all at the same time, in order to really reach towards this vision where people can talk to the robot about everything it can see and everything it can do. Thank you.
I know we're a little late, but we started a little bit late, so we have time for a couple of questions for Stefanie. And do we have the cubic microphones? Oh, so there's a question over there. The blue microphone.
Yeah. All right, Stefanie, thanks so much for the very interesting talk. One question that I had, I agree that robotics is a POMDP, but is human mental modeling a POMDP?
Yeah, that's a good question. Yeah. So I actually think that I guess I'll say it this way. I hope that if we get these hierarchical models right, and I think that there's like a programming language almost for specifying what the human wants the robots to do. And if we get it right, the same model should be able to be used for what the robot can do and what the person also can do, because you can sort of imagine a robot with different capabilities. So I do think I mean, you know, there's duck POMDPs and yes, the real world is multi-agent and stuff like that. But my bet is that we can get a long way by focusing on the single user case where the human's part of the human's mental state is a symbolic expression in a yet to be defined, but we're working on it, programming kind of language, a declarative programming language, a fourth generation language where we're saying goals, not the sort of imperative things where we're saying what we want the robot to do, but we're saying the goals that we want to achieve. And it clearly has LTL in it. It definitely has predicate calculus and lambda expressions, and I don't know what else, but we're sort of working towards that. Yeah.
Question up here.
I think it's really interesting thinking about these problems as a POMDP, but one problem that I can't really find a good solution to is there's a huge space of natural language descriptions for things, and there's also a huge space of descriptions that can go into a belief state. So how do you manage the problem of, at some point you need to query the belief state, and at some point you might need to have several hundred descriptions that have to go into something that can go into like a measurable thing in your state estimator.
Yeah.
So what are your thoughts about?
Yeah, I think that state and action abstraction, or the other way to talk about it is essentially symbols, are going to be key. I really like Mark's talk earlier in the session. We're talking about symbols as ways of factoring or dividing up the state space so that depending on what you're trying to do, different things are active and other things are just, like you could do it if you were asked to do it, but they're not important. So for example, for the speck of dust problem, if you're told to look for the speck of dust, only then do you turn on your dust detector. Only then are there dust speck symbols in your state space. And all the other thousands of detectors you could make are not being run, not active at that time.
All right, we'll take Will and then Rod.
Your talk stitched together a bunch of very different capabilities throughout robotics, and I want to ask about one of the few that you didn't describe how it fits in, which is how robots can learn how to improve their own ability to reason.
Yeah.
So this is related to the symbol question that you were just asked about.
Yeah, so with abstract MDPs, the way that I think of them as they're kind of like a generalization of options. So the trick is that we're specifying at each level of the hierarchy a sub-goal that you're trying to achieve. If you have a policy, whether you've learned it or you've programmed to achieve that sub-goal, great, use it. So you can use any policy-based method for learning robot skills in the framework and sort of plug it in as a solver. On the other hand, if you don't have the policy, or you kind of have a policy, but it may need to be fixed up based on the specifics of the environment, or you don't have a policy, but you have a heuristic, great, we'll use that instead. So actually, I really like your work on the angelic A*. Yes, angelic A*, because one of the things I really liked about AMDPs was to say, well, look, we know A* is really, really good for planning a path to go from point A to point B. Where A* fails is when I'm going to pick something up and then deliver it back there, because for the first part, I'm walking away from where my goal is. The heuristic doesn't work. But if you have a sub-goal, then I have my first sub-goal to get over here. A* works great, I can use it. And then I pick it up, and now A* works great again, I can use it there. So the key idea is abstraction in the form of sub-goals, so that I can use whatever I can think of and basically mine the full space of possible approaches to solve the problem, whether that's a heuristic, whether that's blind search, whether that's particle filtering, or whether that's motion planning, or whatever it is, I can use it. Or learning, you said learning, yes, or learning. And then the other, I'll stop. Okay.
Rod.
Good talk. I have lots of questions.
I'm around all week.
I'm up here in the balcony, in
Okay.
case you're wondering. But the one I really want to ask is, you had inputs that were state inputs, language, and gesture.
Yes.
And I want to know why you want to treat them separately. Why aren't they all just observations?
Well, they are. It's sort of the level of abstraction that you're looking at it at. So at one version of the slide, you guys don't have slides anymore, but anyway, I had they really were all just observations. In the general case, I do think something like speech recognition and human pose tracking should be in the whole model. I don't know, like it does get a little squirrely trying to pass belief all the way down and all the way back up the stack. So the sort of practical reason why they're separate is that the world has created wonderful speech recognizers for us that we don't have to write ourselves. So if we roboticists want to use them, then it's pretty natural to say language is just an input. It comes from Google or Alexa or whoever made the speech recognizer that we're using today. That doesn't necessarily mean it's the right abstraction, but it's something I think is probably not essential to make progress on collaboration.
All right, we got one more question from the blue squishy cube over there. I think this will be the last one. Sorry, I thought there was...
Can you briefly talk about debugging?
About which?
Debugging.
Debugging, okay.
How are we going to debug all this?
That's a good question. Yeah, so I think there's a lot of, I could talk about that for a really long time, actually. I think that at the end of the day, to make the robot do the thing, somebody's got, Nick said this once, somebody's got to sit next to the robot and make it do the thing. And I don't feel like we as a field have, what? You did say.
I say a lot of things. What was I talking about?
We were talking about, we were going to factories and talking about like robot arms doing stuff, and someone's got to sit next to the robot and make it do the thing. Like you can't just put the robot there, it's not going to do the thing. You have to have somebody come and sit next to the robot and make it do the thing. There was a Baxter robot that was in the Museum of Science in Boston running the Intera stack, and they had paid an integrator. The museum people couldn't make the robot do the thing. They had paid an integrator to basically hit some buttons in an open loop kind of a program, because somebody's got to sit next to the robot and make it do the thing. And that debugging process is complicated. One thing that we did is we wrote a programming language to program our robot specifically to make debugging and sort of interactive development faster, picking those magic numbers that we all have to pick, but we don't talk about it, that you need to pick to make the robot do the thing, go faster. The other answer for debugging is abstraction. So if you have the right abstractions, hopefully you can sort of, that naturally decomposes the problem into subproblems. So if you have the right sort of abstraction for moving around or whatever, you can treat that as a subproblem that you're trying to tune, and if there's magic numbers, you can pick them, or if you need to add more training data, you can do it in order to make it work. But I think debugging is probably, I think debugging is probably the biggest challenge for deploying robots today, because there's so many systems that can go wrong. Thanks.
All right. Well, thank you very much, Stefanie. And I'm going to give the mic to Nate, who has a few announcements. Thank you, Steph. Can I give you this?
Okay, that was a great talk. All right, we're about to move on to the poster session. I just wanted to go over a few items. First, for those of you who have not yet realized it, you have free museum admission as well. You just need to show your name tags. So there are two museums here, the Carnegie Museum of Natural History, as well as the Carnegie Museum of Art. So feel free to visit. There are lots of places to explore, lots of exhibits to see. Just a reminder, Families at RSS is still going on, and if you're interested in childcare, please reach out to Matt. This evening, we have several activities that are happening concurrently. First, we have the Pittsburgh Robotics Showcase, and this is sponsored by Bosch. Second, the RI Open House, and third, tours of NREC and Uber ATG. The Pittsburgh Robotics Showcase and the RI Open House are both going to be located at Newell Simon Hall or the Robotics Institute over at CMU. If you do not know how to get there, there will be some volunteers to direct you. The tours of NREC and Uber ATG will be enabled via shuttles. Thanks to all that confirmed, the list's finalized, and you should be able to see it via the same link as before. There are two groups. There are 4 shuttles. Your pickup location will be where the yellow arrow is indicating. For those of you that are familiar with this area, that is along Forbes in front of the Gates Hillman Center. There will also be volunteers located there. It's about maybe a 5 or 8 minute walk if you're walking slowly. So, yep, actually that's what Google reports as well. Okay, in terms of the RI lab tours, many of you signed up when you came in and checked in. If you've forgotten what labs you're on or lab tours you're on, you can go back to the registration and check-in tables and see what lab tours you're on. But there are 3 different times, many different groups, and each of those tours will be visiting different sequences of labs. Please make sure that for both the NREC Uber tours as well as for the lab tours, that you show up at the desired tour start location a few minutes before the noted times. That's it. Enjoy the poster session.